So I work at KTH in Stockholm. I'm the director at the Nuclear Energy Engineering Master Program, and I teach reactor physics and Monte Carlo methods in nuclear engineering. So today I'm going to give you the lecture on aspects of steady-state coupled Monte Carlo simulations. It will be primarily about numerical methods that are involved in the coupling of solvers, criticality solver and solvers that describe different feedbacks in order to achieve steady-state conditions. So just a quick outline of the lecture. I will specify the problem in more detail, then I'll just show a few very simplified equations. I will present the numerical test solver that I'm going to use for the animations and the plots demonstrations. And I will show you a number of ways in which people have been trying to calculate the steady state. Many of the ways are not optimal, and I will show you why. But at the end, I will show you also how you can achieve the steady state in a proper way, efficiently and maintaining numerical stability. So let's start with the problem specification. So we are dealing with reactivity feedback. So I suppose you all are familiar with what the feedbacks are. Basically, at any moment when the reactor power change will affect the reactivity in the system, we can say that we have reactivity feedbacks present, because when the reactivity is changed by the changes in power, that will in return cause changes to the power itself. So we have a loop which may converge or diverge, right? So here's just an example of some common feedbacks, like feedback from the fuel temperature. And this is known as the Doppler feedback. It's very fast feedback. It's acting almost immediately in the reactor. Most of the feedbacks are slower, like the feedback from the coolant, which we call delayed because it acts with some delay, about a second or so. This is simply because it takes time for the heat to be transferred from the fuel into the coolant, and it may take some time for the, for instance, for the bubbles in the boiling water reactor to get transferred from the bottom of the core to the top. So different systems will have different delays in the coolant temperature feedback. We can also think about the feedback coming from some fission products like xenon 135 or samarium. These act with much longer delay, a couple of hours or days. And we can also consider the fuel depletion to be a feedback acting with a delay of several weeks or at least a couple of days. Right, so we have different delays in different kind of feedbacks. So that's important to remember. Now we can also sort out the feedbacks into positive and negative. So whenever the positive change in power causes positive change in reactivity, we basically say the feedback is positive. And these are dangerous feedbacks because a positive change in reactivity will trigger further positive change in power, which will combine with the original positive change, and well, this will never stabilize. So it's an unstable system. The same unstable behavior you could also observe if the initial disturbance was in the negative direction, like if you drop the power in the system with just positive feedbacks, then you would trigger negative change in reactivity, which would amplify the original negative change in the power. So the reactor would shut down itself. Yeah. So you don't want to have positive feedbacks in the system, and we usually don't have strong positive feedbacks in the system. I mean, not in the current existing reactors. But you have to be careful. In principle, they exist. If you use some exotic fuels, you may get them. So I'm not going to treat systems with positive feedbacks because all the numerical methods for coupling of the solvers that I'm going to talk about will assume that all the feedbacks are negative. All right. If you wanted to work with system with positive feedbacks, you would have to make some slight modification to these methods. But I'm not going to consider that today. So I'm going to assume that all the feedbacks that we have are negative in the system, and they may have different delays. Okay? So when you have negative feedbacks, that means a positive change in power will trigger a negative change in reactivity. Now, when you drop reactivity, you'll be dropping down the power. So that will act against the initial positive change in the power. And you may find the system will eventually stabilize, hopefully, not always. It depends actually on the time delay with which the feedback acts. But if you have very fast negative feedbacks, then your system is almost always stable. When the delay is larger, like a second or more, then you may actually observe some instabilities in the behavior of the reactor. So you have to be careful with this. You know, when the delay time is very large, like an hour or more, and then the reactor operators, they have time to actually stabilize the system. So it's not a big issue for the operators. But when the delay is relatively short, like less than a second, or in terms of seconds, and then that may be a problem to stabilize the reactor, and the reactor very often has to be shut down. All right. So I'm going to work primarily with negative feedbacks with longer delays today. But the methods that we will look at, those are used for feedbacks with any kind of delay time, yeah, short or long. All right, so let's define equilibrium points. So it is basically a point in the phase space of the system. So basically a set of conditions in the reactor at which the reactor can maintain a steady power over time. Now, mathematically, you can actually locate equilibrium points, or we can call them steady state conditions, in any reactor, irrespective of whether the reactor is stable or not. Yeah, when the system is unstable, after basically any disturbance to the equilibrium point, the system would diverge from the equilibrium point. Yeah. So even though the equilibrium points exist in unstable systems, they will basically not, the reactors will not maintain the equilibrium in reality. Yeah. On the other hand, when the system is stable, whenever you have this stable reactor running at some power and you introduce some disturbance to the system, and the reactor will tend to come back to its original state, to the equilibrium state. Yeah. So that's how we want that our reactors would respond. All right. So that was all what I wanted to say about the feedbacks. Let's have a look at different kind of problems that people are currently trying to use the Monte Carlo methods for. So the basic one is a fixed source problem. It's very simple mode of calculation for subcritical systems when you locate your external source of neutrons in the system or outside, and you basically start all your neutrons from that location. It's not computationally expensive to solve this problem. So when we are talking about Monte Carlo methods, I assume that you all are familiar with the theory. Basically, we are simulating a large number of individual neutron histories in the system. You have to know the scattering laws, the cross sections for different energies of neutrons, and to know the position of the neutrons where they start the fission source. So for fixed source problem, the simulations are quite easy. And then we can have criticality problems. Basically, these are problems when the distribution of fission neutrons is not known, like in your nuclear reactor. If you just know the geometry of the reactor, you don't really know how you should distribute your fission source in the core. So you basically need to iterate the distribution of the fission source over a number of steps. In Monte Carlo terminology, we call them cycles, criticality cycles. I'm going to mention this term criticality cycle a couple of times during my presentation. So I just want you to remember that that refers to the criticality calculation. We are iterating the fission source distribution. Right, so basically at every cycle, we start with certain location of the fission neutrons. We simulate the individual histories of these neutrons, and we simulate the fission reactions, and that allows us to sample a new distribution for the next generation fission source, right? So after a number of criticality cycles, the fission source converges into a steady state for certain fixed geometry. So the criticality problems are a little bit more difficult than the fixed source problems, but we assume that they are done in systems without feedbacks, right? So basically the system doesn't change. So the problem is linear. So more problems appear when you introduce feedbacks in the system, right? So you want to find steady state power distribution, for instance, in the reactor in which feedbacks are present. So typically running power reactor will have quite strong feedbacks, and they have to be taken into account when you want to calculate the steady state power distribution. So this is the problem that I'm going to talk about today: how to achieve this steady state with the consideration of presence of the feedbacks in your system. Now, there are many other problems, like I believe yesterday you had a presentation about kinetic calculations with Monte Carlo solvers. So these take into account the time dependence of the neutron flux for very short time problems, a couple of seconds or minutes. And you have to take into account the presence of precursors of direct neutrons when you want to simulate such a system. You can also try to solve a dynamic problem similar to kinetic problems, just you have to consider also the presence of the feedbacks. And very common is also to see the application of Monte Carlo methods to the depletion problems, right? So these are solved by so-called Monte Carlo depletion, Monte Carlo burn-up codes. most of the codes currently used, they include equation solver. So they may or may not take into account other feedbacks than from the field equation, like the thermohydraulic feedback as well. Although it's not very common nowadays to see such simulations yet. All right. Well, there are many more other problems in reactor physics, but these are like the list of problems that Monte Carlo methods are used for most of the time. Right, so this I already mentioned that basically what we want to calculate now is mainly the power distribution in a running power reactor, a reactor with strong feedbacks. So definitely we need some tools, some computational tools like a criticality solver that will give you power distribution for a system with some fixed, for some given conditions. So in our case, that would be some Monte Carlo code like MCMP or Serpent. There are many codes nowadays you can choose from. And then we need some solvers that will describe the reactivity feedbacks, right? So it could be like thermohydraulic solver or any solver that would give you the feedback conditions. Let's have a look at some equations. I'm not really going to show you many equations. So they're going to be actually incredibly simplified. I couldn't simplify them more, as you'll see. So these are the variables that I'm going to work with. The temperature field, so I'm going to denote it by T, depends on the location in the core. Right, I'm only going to use the temperature field as the feedback example in my equations, but well, we can just generalize the outcome equations for all the other feedbacks. It will just keep the equation simple when I use only the temperature field. And then I'm going to work with the neutron flux. So I'm going to denote it by phi. Also, you'll see the dependence on the space location in this neutron flux. Although in principle, there are many other dependencies like on the angle and the neutron energy. But for our purpose, I'm just going to work with the position dependence. And I'm going to assume that all the other dependencies on the direction and the energy are integrated. All right, so next, let's denote the fundamental mode neutron flux in the system by phi node. And it will be dependent also on the given temperature field in the system, right? So if the system has the temperature feedback, then the neutron flux will depend on the temperature field. So I'm going to include this dependence in the flux. So the fundamental mode basically means that it is the steady state flux in the system with the given temperature field, right? Because when you basically write down the criticality equation, mathematically you'll see that there are many other solutions possible. It's an eigenvalue equation. So there are two unknown quantities, the flux and the eigenvalue, but there's just single equation for it. So actually indefinitely many solutions to the equation. Only one of them is physically meaningful. It's non-negative in any point in the system. So we call that fundamental mode. But you know, it's the single solution that makes sense from the physical point of view. And then I'm going to denote the criticality solver by S phi. Yeah, so S like solver and solver for flux. Right. So that will basically return the fundamental mode flux for a given temperature field. Right, so I'm going to write this equation. It's kind of like the criticality equation, very simplified here. Now I can write similar equations for the temperature field. So let me denote the steady state temperature field in a system with a given neutron flux as T infinity here. Right, so that would be basically the temperature field that would get established in the system in which we have specific given neutron flux distribution. Yeah. And then I'm going to denote the solver for the temperature field by ST. All right. So then I'm going to write similar equation as I wrote for the flux for the temperature field here. Basically, the temperature field, the steady state field for the certain flux is going to be given by the solver, the thermohydraulic solver, and that is taking the flux as the input. All right. So let me take again the criticality equation, the neutron flux solver equation, and let's introduce the feedback in it. Right, so the solver is taking the temperature field as the input. So now I'm going to claim that this input must be actually the steady state temperature field that corresponds to the fundamental mode neutron flux that we actually want to be calculated by the criticality solver itself, right? So we want that the criticality solver calculates the fundamental mode flux, but as you can see, the fundamental mode flux is actually used as the input for the solver itself, right? Because it's needed to calculate the steady state temperature field, which is used as the input for the criticality solver. So instead of the infinity, I'm going to write the steady state temperature field solver here. So now we have like two functions here. I'm just going to simplify it. I'll write G instead, right? So these two functions together are defining this G function. So that will simplify this equation into this one. So it's basically a general nonlinear equation, which may or may not be easy to solve, right? It depends on the nature of the equation. Some nonlinear equations are easy to solve and some are not. And that's basically the same situation for the problems in vector physics. Some of the nonlinear problems are easy to solve and some are not. And it depends on the complexity of the problem and the size of the problem, right? So we will see that today as well. Now, before I start to talk about the numerical methods or the coupling schemes by which we couple these two solvers, let me just introduce the numerical test model that I'm going to use today for the demonstrations. So, you know, whenever you want to demonstrate some phenomenon, you want to use extremely simple numerical model that basically people can easily reproduce. It's perfect to use just 1D model. It makes it easy to plot the result because you just need, you know, simple 1D plot for that. And I'm going to use homogeneous lab. Homogeneous, well, actually it's not correct because I'm going to be changing some conditions at different location, but the initial start, the initial state of the system is homogeneous. It's a 350 centimeters wide slab reactor with 0 boundary conditions. So basically, I just state that the flux at the boundaries is 0. And the material composition is given by this table here. It corresponds to a material that you would get if you homogenize standard fuel cell from a pressurized water reactor, right? Although I didn't include the, like zirconium here, so it doesn't really react much with neutrons. But uranium is more latent hydrogen than oxygen. And I also include xenon because I'm going to use xenon as the feedback for my solver. And here are the cross sections that I use and the new bar. So let me explain what criticality solver I use for these numerical tests. I'm actually not going to use true Monte Carlo solver. I'm going to use a fake one that I programmed. It's basically a simple diffusion-based solver, one group, 1D solver. So it's very easy to program this. But I'm going to introduce random noise in the solutions. So basically, when you are using the diffusion solver at each criticality cycle, you can use the solution for the neutron flux and use it as a probability density function to sample the fission source for the next cycle, right? So if you get some solution for a specific cycle, you can use it as a distribution from which you sample randomly the location of neutrons, fission neutrons for the next cycle, right? And then you basically simulate the next cycle with this randomized fission source. And you apply again the diffusion solver on it. So this has some advantages because I can actually switch off the random noise from the solver if I want to, right? So that will make it easy for me to get a good reference solution, and it will also make it easy for me to see the effect of the random noise in the actual convergence of the calculations, right? I want to demonstrate that it actually works similarly to real Monte Carlo solver. So I will show you the convergence of the fission source when the random noise is not switched off, of course. So I will use 1,000 neutrons per cycle. So the batch size is 1,000. And you will see this video on the left-hand side. You will see the distribution of the fission source at every single individual cycle. So that will be very noisy because you have just 1,000 neutrons per cycle. But you will see how it changes rapidly over the cycles. On the right-hand side, the blue plot shows the distribution which is averaged over all the simulated cycles, right? So basically, when you run your Monte Carlo simulation, you are averaging the results over a number of cycles always. That's why you are running many thousands of cycles almost always. You want to minimize the standard deviation in the mean value, right? In the value that you averaged over all the cycles. So you will see that the distribution of the neutrons over the system will actually converge on the right-hand side. So this is the, I call it cumulative source. Yeah. And now you see it's not actually scaled to the same value. This is for cycle 1. I mean, the scale doesn't matter. You can basically scale power distribution to any value in criticality calculations. So this is not really an issue. So I will play it now. Right, so you can see the cycle number here for the source in individual cycles, and also for the averaged fission source. So actually, you couldn't distinguish such results from a real Monte Carlo solver, because if you plot the distribution of the fission source from a real Monte Carlo solver, it looks just like this. Yeah. Now, of course, if you choose a larger batch size, like 1 million neutrons per cycle, you will see much less noise in this red distribution, right? Now, if you have a small batch size, like in my case, just 1,000 neutrons, that doesn't mean that you will not achieve a very good converged solution. As you can see on the right-hand side, the solution converges very well to the cosine. That is what we expect, right? Although the number of cycles is quite large now, it's like 250,000 cycles. So of course, if you choose a larger batch size, larger number of neutrons per cycle, you will not need as many cycles to achieve a small deviation for the averaged fission source. All right. Now, I suppose we will do the question answer session at the end, but I mean, if you have some question now, you can just ask me, all right? So that was the criticality solver. Let's take a look at the solver that I'm going to use for the feedback. I'm not going to use the thermohydraulic solver for the temperature field because I'm going to use the xenon 135 feedback in my test calculation. And the reason for this is that the solver for the xenon concentration is very simple. It's given by these equations, which are much simpler than the equations for thermohydraulics. And at the same time, the feedback from xenon is very strong. It's strong negative feedback, and it acts with a large delay. So that's always nice because that gives you some opportunity to demonstrate some instability issues, right? So the concentration of xenon is given by these two equations. You can see it's a coupled system of ordinary differential equations for xenon 135 and iodine. The iodine equation is needed here because the iodine is one of the sources of xenon. Iodine decays into xenon. You can see it from this equation here. The decay of iodine is used as a source term for the xenon. Iodine can be produced directly from fission, as you can see here. If you look at the equation for xenon, we see that it also can be created directly from fission at different yield. And then it is removed from the system by decay. Its own decay, it's like 9.2 hours half-life. And it can also be burnt out, yeah. So by neutron capture on xenon, it is transmuted into a nuclide that doesn't absorb a neutron as much, right? Now, for our purpose, we want to get solutions which are steady state for a given neutron flux. So, so what we can do, we can just set the left-hand sides of both equations to 0, and we can solve the algebraic system of equation. Very simple because there are just two equations here. So you will get this result here. So the steady state distribution of xenon depends on flux via this equation. Now, if you plotted this equation, you would see that for a smaller neutron flux, you will get a smaller concentration of xenon. But as you start to increase the neutron flux, the concentration of xenon will grow slower and slower. And at some point, it will hit a limit. You can see it from this equation. If you set flux to infinity, right, you'll see that there is actually a limit to the value for the concentration of xenon. But this is really theoretical. In principle, if you had such a large flux in your system, then you would also have to introduce another term in the equation for iodine here, because you would start to burn out iodine as well. I mean, it has a small neutron absorption cross-section, but it's not zero. So for very large neutron fluxes, the absorption of neutrons on iodine would have to be taken into account as well. But that would be flux that would not be really feasible in existing power reactors. So that's why I don't consider that situation. So I just want you to remember that for larger fluxes, we get larger steady state concentration of xenon, but the function is not linear. Yeah. So let's denote this concentration as saturated concentration for the xenon. There are a lot of confusions here because sometimes people think that when it's saturated or steady state, it means that it is in steady state with the neutron flux as well, which it is not. So let's assume that the saturated concentration of xenon is simply the steady state concentration in a reactor at which the flux is fixed. Yeah. So I assume here it is fixed, it doesn't change. If it did change in response to the concentration of xenon, you would again have nonlinear equation here. Yeah. So so I'm going to make a distinction between saturated concentration and the equilibrium concentration of xenon. So when I talk about equilibrium, it means that the flux is not fixed and it responds to changes in the concentration of xenon. All right. So, even before I tell you how you can calculate the steady state or the equilibrium state, I will show you right away how it looks like in my system, in the slab reactor. So if you take a system without any xenon and you calculate the neutron flux, you will simply get the cosine solution, right? So that is the solution for a slab reactor, and that all of you are familiar with. As soon as you consider xenon to be your feedback in the reactor, and you try to achieve the steady state with the consideration of xenon feedback, and you achieve the steady state, you will get the red solution here. So you see that it's very different to the cosine. I mean, it still has a top in the center, and it's smaller, close to boundary, but it's much flatter than the cosine shape, right? So this is because if you look on the right-hand side plot, you'll see this is the equilibrium distribution of xenon in the slab. And of course, it has the largest concentration in the center and smallest towards the boundaries. So naturally, the neutrons will be affected by that. Yeah, more neutrons will be absorbed on xenon in the center than in the location close to the boundaries. So the neutron flux naturally will be lowered in the center, right? So this is basically the solution that we are after, right? The flatter one. All right, so there are a number of ways how people have been trying to achieve the steady state solution. And one natural approach to calculate the steady state is simply by running a transient calculation. And in this case, you would couple basically a method that solves ordinary differential equations. So there will be some solver for the feedback and for the criticality solver. You would discretize the time into short time steps. So in case of the xenon feedback, you would have to have time steps which are much shorter than the delayed time with which the xenon feedback acts in the system. So in my case, I used 20-minute time steps, which is short enough to get a smooth transient solution. And you would have to use, of course, the equations for the time-dependent concentration of xenon and iodine, not for the saturated concentration, right? There are different coupling schemes. I don't really want to focus on the coupling schemes for the ordinary differential equations because the transient simulations are not the best way to achieve steady state. But there are different schemes like implicit and explicit Euler schemes. You can basically use any of these for these simple demonstrations. I'm going to show you 4 different animations here. The transient solutions for the slab reactor, and I will vary the dimension of the reactor from 2 meters to 5 meters. So the 2-meter slab is quite small. But the 5 meters, it's much larger. You will see that it makes a big impact on the transient solution. So you will see this arrangement in the videos. The blue curve will be xenon 135. The neutron flux will be the black line, and iodine will be the yellow line. And in most of the animations, I will start with asymmetrical distribution of xenon to make the animation more interesting. And now, of course, when the transient converges, it will converge irrespective whether you start from flat distribution or from a disturbed distribution of xenon. But it makes the animation more interesting to look at, right? So when you start with this asymmetrical distribution of xenon in your system, you basically load the left part of the reactor with lots of xenon. If you calculate, the neutron flux in such a system, naturally, the flux will be primarily present in the right part of the reactor, right? So let me play these animations here. Right. So you can see that you can see the time here. It's still running, but you can see that after like a day or two, we actually achieved the steady state solution. So the calculation converged, and you could use this as your solution for the power distribution, right? So we have the flux here. So you could use that to calculate your power distribution in the system. So the simulation is stable, but remember, this is a small system, just 2 meters wide slab with 0 boundary conditions. So the dominance ratio of the system is very small, and all the methods converge depending on the dominance ratio of the system. So the only issue here is that you would actually have to specify quite many steps, time steps, to achieve the steady state, right? So this could be computationally quite expensive way to calculate the steady state, even for a system in which it converges. Let's take a look at the 350 centimeter wide slab. So we can check the time. Now it's 2 days, 3 days. I can tell you right away, this transient doesn't converge. It continues like this forever. The system is not stable. So you see you have a system here which has a strong negative feedback, and it's not stable simply because the feedback acts with a very long time delay. And whenever you have negative feedbacks with long time delays, the system may become unstable. But it doesn't depend only on the presence of delayed feedbacks. It also depends on the size of the system. So in the same feedbacks were present in 2 meter wide slab, but you could see it converged in that system, while it doesn't converge in the larger one, right? You can see that the flux always moves to the location where there is smallest amount of xenon, right? But when you have a large flux in some location, then you will eventually generate a lot of iodine in that location, and that iodine will decay into xenon. So after some time, the xenon concentration in that location will grow, and it will force the neutron flux to move away from that location. So that is basically the mechanism behind these xenon oscillations. Right, so you know that xenon oscillations, they really exist in thermal power reactors, and the reactor operators, they have to stabilize by control rods these oscillations, right? But they are lucky because these oscillations have very long periods, so operators, they have a long time to act. Let's take a look at 500 centimeters long slab. It doesn't converge either. Of course, the oscillations are even more severe. Now, you may now suggest that these oscillations are triggered by the initial asymmetrical distribution of xenon. And you may think that if I set, zero xenon in the whole system, that we wouldn't actually see these oscillations. I can prove you wrong. So I will show you the last animation where the xenon is actually set zero concentration in the whole system. Now at this point, actually, I'm going to pause it now. You could think like the simulation is converging because the solution looks quite good here, but you can see small movements in the distribution, right? And it looks like it may start to develop some kind of symmetrical oscillatory mode, but as you can see, it flipped into side-to-side mode, right? Because the side-to-side oscillation mode is actually the dominant mode here, although the system is able to oscillate in the symmetrical mode as well. But when the flux has the option to actually move freely left to right, then it will do that. It's a dominant mode here. All right. So the system is unstable, and you will get this oscillation even if you start with symmetrical initial conditions, right? Eventually, there will be some tiny asymmetry due to the round of errors in the neutron flux, and the flux will, after that, very quickly flip to one side, and it will start to oscillate. All right, let's come back to the presentation. So I would not recommend you to try to calculate the steady state by running transient, because more than likely it will not converge, depending, of course, on the size of the system and the nature of the feedbacks that you are simulating. But if you are simulating large vector with strong negative feedbacks, you will run into instabilities. All right, so let's take a look at some well, I don't want to say better methods, but let's take a look at some other methods. We can apply the fixed point iteration directly on the nonlinear equation. So you may think like that may actually be more efficient because we don't have to run the transient calculation. We can use the we don't have to use the ordinary differential equation for the feedbacks. We can use the equation for the feedbacks that give us the saturated xenon conditions right away. Right. So when you apply the fixed point iteration on the nonlinear equation, you basically introduce iterations. You iterate the flux and the conditions in the system according to this iteration scheme. So basically you start with some guess for the neutron flux. Very often it would be a flat function for the whole system. And you would use, so that will be this the phi 0 here. You would use that as a input for the G function. So basically that means that you would use that flux for the input of the thermohydraulic solver to get the temperature field, the T infinity, and then you would use the T infinity to model the condition in the reactor, and you would calculate the flux phi 1, right? And you would use the phi 1 flux in the next iteration step as the input for the G function. And then you would repeat these steps over and over until hopefully you would converge the system. So I'm going to show you plots now of the fixed point iteration for the system that is 350 centimeter wide slab, right? So it is the system that actually the transient calculation diverged for it. So I will show you the deterministic mode first. So I will switch off the random noise in my solver. So you can see here step number 1, step number 2, step 3, step 4. The black line is the neutron flux, and the blue line below is the distribution of xenon in the system, right? So you don't see the flux phi node, the gas, which was 0. You see the step 1. So what you can see here that doesn't look very nice. The error doesn't seem to actually get any smaller. It's around 15 to 18%. And you can see very clearly why we have this stability issue, right? So this neutron flux was calculated in the reactor without any xenon, so it's cosine shape. That's correct. So based on this neutron flux, we calculate the saturated concentration of xenon, which looks like this. It doesn't look exactly like cosine, because remember the function for the saturated xenon concentration was not linear with respect to flux. But you can see that the xenon concentration is bigger in the center and it's lower at the boundary location. So when you introduce the xenon distribution in this shape into the reactor and you calculate the flux, neutron flux in the system, naturally the neutrons will be absorbed on xenon in the center to a larger degree than they will be absorbed in the locations that are further away from the center. So that's why the neutron flux will have actually peak not in the center, but further away from the center, right? So again, you will use this neutron flux distribution for your feedback solver. So in our case, the xenon solver. So it will have a similar shape to the neutron flux. And you will continue to the next iteration step. You will introduce this distribution of xenon into the system. You will not surprisingly get flux, which has a center. It has a peak in the center because you can see that the xenon distribution in the center is actually smaller and then further away from the center, right? So this will continue like this for some time. I'm going to show steps 97 to 100. You will see that the oscillation mode actually flipped to the side-to-side mode, which is the dominant one in the system as well. And this oscillation doesn't converge. So this iteration based on the fixed point iteration does not converge for the system. Right now, if it doesn't converge for a deterministic solver, it's not very likely to converge it for Monte Carlo solver either. But let's just take a look at it if it's really true. So I switched on the noise here in my solver, and you can see actually a very similar mode of oscillations. It looks like just the noise is superimposed on the solutions. And yeah, I mean, they are more asymmetrical than in case of the deterministic solutions. If we move to steps 97 to 100, you'll see that the solution flipped to the side-to-side oscillatory mode as well here. And that's not good, right? You don't want to get a solution at the end of your advanced Monte Carlo simulation that will have 30% error at the end. So it's a problem. The fixed point iteration may diverge. Again, it may not. It depends on the system, on the nature of the feedbacks, on the size of the system. But it's a problem in general, not only because of the possible instability, but also because when you look at the final solution, so we take solution from step 100, you will see presence of the random noise in it. And this random noise will always be given by the neutron statistics from the last cycle, right? So if you use only 1000 neutrons per cycle, and the standard deviation in the solution will be given by 1000 neutrons. So that's very poor statistics. You would have to use a very large number of neutrons per cycle to lower it, and you would spend a lot of computational time on that. So it's not stable, and the fixed point iteration is not efficient either. So it's not suitable for coupling Monte Carlo criticality solver to the feedback solvers. So I do not recommend it. So how can we stabilize the simulation? Well, a natural approach to stabilize the fixed point iteration is to introduce the relaxation scheme. So you can apply the under-relaxation scheme on the solution, right? So the under-relaxation looks like this. You will basically set a so-called step size parameter alpha. So for instance, the step size is in the range 0 to 1. So we can choose 0.5. So if you choose 0.5, then it means that we are going to be combining the iterated solution from the previous cycle with the solution that you get from the G function. Yeah, the latest solution that you get from the G function. So you take 50-50, for instance. So that may help with the stability. Now we can rewrite this equation in this form. It's exactly the same equation. And usually you can see this equation rather than this one, because the lower form of the equation looks a little bit more scientific. So people will usually write it like this. I prefer myself to write it in the upper form, because I mean it makes it very clear what is happening, right? What exactly you are doing. So let me show you the plots from the deterministic solver. So I am switching off the random noise again here, and I'm setting the step size to 0.5. So you may be very happy now at this point to see that it appears as if the calculation converges, right? We start with the error 8%, and it drops very quickly. I mean, this is a very small fraction of 1% here. It looks like the correct solution. Let's take a look at steps 10, 20, 30, 40. It looks like the solution is converged. It doesn't improve any further, but that may be just some kind of round of error in my reference solution. Now, when we run Monte Carlo steady state calculations, we always have to run many iterations to improve the statistics. So let's take a look what happens if we actually run more steps here with the deterministic criticality solver. So here you can see results for steps 50, 60, 70, and 80. And something weird is happening, isn't it? You can see that the error at step 70 starts to grow. And at step 80, it becomes much larger. I mean, when you compare it to between step 60 and 80, the relative error grew by 3 orders of magnitude. So something is wrong here, right? Let's take a look at step 84 to 87. You can see that the relative error continues to grow. At step 87, it's already significant. So you can actually see the error visually. And when you compare the steps 85, 86, and 87, you'll see that the neutron flux actually oscillates side to side. Quite small oscillation, but it is visible. I mean, I hope you can see that. Let's have a look at steps 97, 98, 99, and 100. And you can see now clearly that the solution is definitely oscillating, and the error grew to 8%. Now, how is this possible? The solution appeared to be convergent during quite many cycles, like until cycle 70 or so, and suddenly it diverges. What do you think? So the reason for this is that we started with a neutron flux that was flat. That was the initial gas. It was flat, so it was symmetrical. But this system, 3.5 meter long white slab, is actually unstable. But it is not possible actually to see symmetrical oscillations in this system. The only mode of oscillations that it can support is the side-to-side oscillation for the neutron flux and xenon. Right? If the system was larger, it would support the symmetrical oscillations as well, but this system cannot. So it actually took quite many iteration steps before the round of errors made the solution very slightly asymmetrical. And once that happens, the asymmetry starts to grow in the neutron flux distribution over the cycles, over the iteration steps. And eventually, you'll see the error visually like this. Now, as you can expect, if we choose the Monte Carlo solver, there'll be a lot of noise in the solution from the start, and the solution will not be symmetrical. So you may expect that this development of the instability in your iteration will happen much earlier. You don't have to wait until step 80 to actually start to observe some oscillations. So let's take a look at that. I will show you other slides. So it's the same scheme with the same step size, 0.5, but I'm switching on the random noise. I'm using 1000 neutrons per cycle. At each iteration step, I'm running 500 criticality cycles. That is also true for the deterministic mode. All right, so here you can see step 1 to 4. It looks pretty wild. Can't really say it's unstable yet because there is so much noise in the solution. But here maybe you can say that we have a strong left to right movement for the neutron flux. So that may be caused by the feedback. Let's take a look at further steps. Yeah, I mean, that seems to be happening. We have left to right oscillations already, and it's quite pronounced. But the noise is very large as well. Here you can see steps 97 to 100. It doesn't look like it's getting much better. The noise is very severe, and we seem to have the stability issue here. Now you may say that it may require many more iteration steps, but we will see later that that is actually not the case. So it didn't really work with the step size 0.5, neither for the deterministic and the Monte Carlo mode. Let's try to lower the step size to 0.2. That may help to stabilize the iteration. So here we have the deterministic solution that seems to be stable here. And I simulated only 100 steps. It seemed to be stable. Now it's probably not stable if I run many more steps, like if I run a couple of thousand steps, more than likely the left to right oscillation would develop. It will be damped down quite a lot because the step size is 0.2 only, but eventually it would happen as well. But you know, if you were using just the deterministic solver and you run 10 iterations, you will get very good result with this. Let's take a look at the Monte Carlo mode. The step size is 0.2. I'm using the same 3 parameters as before. So we have first 4 iterations. We can't really see much, except that you can see that the neutron flux doesn't change as much. That's simply because the step size 0.2 is introducing quite small changes into the iteration after each step, right? The flux can change only by 20% now, right? So that makes it slower to converge, but it makes it more stable. The iteration is more stable as well. Let's jump to steps 97 to 100. You can see that the error stabilized at about 3 to 5%. It's not great. There is quite a lot of noise and possibly some instability. For curiosity, let's take a look at steps 997 to 1000. So I simulated 1000 cycles here. You can see that the error didn't really improve. You know, I made 900 more iteration steps, and the error is still in the range of 3 to 5%. Now, this is partly because there may be still some oscillatory mode present in the solution, but also there is an issue with with the random noise is actually quite constant. It doesn't really decrease over the iteration steps. This is because you are always taking 20% from the last Monte Carlo criticality solution, right? So you are running the Monte Carlo solver with a certain number of neutrons, right? In my case, it is 500 cycles with 1,000 neutrons. So it's 500,000 neutron histories for the slab system. That will give you quite a large noise in the solution. So we are taking 20% of the noise and we are putting it directly into our result. So the result will always contain a fixed amount of noise from the last Monte Carlo solution. So in fact, the relaxation scheme cannot converge in principle because it will always contain a fixed amount of random noise in the solution, right? So if you wanted to achieve a better solution, you would have to simulate more cycles at every criticality calculation, and that would increase the cost of the whole simulation a lot. I will quickly show you the animation. It's the same result, just animated here. So you can see that the random noise, that is basically this noise in this black line for the neutron flux, doesn't really get smaller with the iteration steps, right? It looks to be constant. So that is a problem. Your simulation will never converge. All right. So this I mentioned, the problem with the relaxation scheme. Let's take a look at the last scheme, the stochastic approximation. So this is going to be the scheme that will likely work for us. It is a relaxation scheme as well, with the only difference that the step size, the alpha parameter, is not fixed, but it's allowed to actually change over the iteration steps. So it will start from a large number and it will decline, it will drop down step by step, right? So if you simulate large number of iteration steps, it will the step size should drop to a very small number close to zero. Otherwise, the relaxation scheme is the same. I also introduced this d parameter here, which should be chosen from the interval 0 to 1. I will talk a little bit about this later. How can you control the step size value? You can, this is the simplest way to assign a value to the step size is to use the Robbins-Monroe algorithm for it, which is very simple. You will just basically take 1 over n, where n is the index for the iteration step, right? So iteration step number 1, the step size will be 1. In the second iteration step, the step size parameter will drop to 0.5. In the next one, it will drop to 1 over a third, and so on. Now, if you substitute 1 over n to this equation, you'll actually see that you can transform the equation into this form. Now, when you look at it, you'll see that the solution for the neutron flux is actually combined from the individual Monte Carlo solutions from all the previous steps with the same weight, right? So we are actually averaging all the solutions from our Monte Carlo solver over all the previous iteration steps, and we are assigning the same weight to all these individual solutions. I will only demonstrate it on the Monte Carlo mode, but actually it converges for the deterministic mode as well. So let's take a look at the results here. So of course, in the first steps, you will just see the random noise. So there's nothing interesting here. If we move to steps 97 to 100, you can see that actually it works, right? The error drops. It's 0.5% here. It doesn't oscillate. If we continue to steps 997 to 1000, you can see that the error continues to decrease. So it's 0.27% here. And it looks quite well. It converges. And because you are combining all the solutions from the Monte Carlo solver together over all the iteration steps, you are also combining the random noise together. Now, you know that when you are combining the random noise together, the random noise will be eliminated from the solution to some measure, because the random noise means that the noise increases the solution in positive or negative direction, right? So if you have many positive and negative deviations from the mean value, they combine together to 0. So by combining all the solutions together, you are actually not only stabilizing the iteration, but you are also reducing the random noise in the solution. Let me show you the animation. So it's the same calculation, just, you can see the result in this animation. It is the index for the iteration steps. Right, so you can see that it slightly moves. I'm not sure you can see the tiny movements. Slightly moves. The movements are getting smaller and smaller. The solution is absolutely stable. The random noise is getting smaller and smaller. So that's definitely working. And the stochastic approximation definitely works. So there are still some parameters that you have to decide on when you are using the stochastic approximation, like the value of this d parameter, which is interesting. If you set d at very small value, like 0.1, basically it means that the initial guess will have a large impact on the solution in the first steps. So if you are just guessing the solution, like you guess the solution is, the power distribution is flat at the beginning of your calculation, I would recommend to set the d parameter at 1, right? You still have to choose the efficient source in each criticality calculation. I would recommend that you choose the efficient source distribution that was iterated in the previous criticality calculation. That way you will get much faster convergence in the criticality calculations. And another interesting topic is how to optimize the statistics, right? So basically the number of neutron histories that you simulate at every iteration step, right? Like every time when you run the Monte Carlo criticality solver, you have to decide the number of cycles and the number of neutrons that you simulate at every cycle. So I mean, you have a choice to use small number of cycles at every time you run the Monte Carlo criticality solver, but then you can compensate it by running more iteration steps for the coupling scheme, right? Or you can do it vice versa. So which option is better? That's an interesting question. And I would say the answer to this depends on the nature of the feedbacks that you are simulating. If your feedbacks require a solver that takes a lot of computational time, like some thermohydraulic codes, then they may take a lot of time depending on how much you discretize your system. Then it may be beneficial to have fewer iteration steps in the stochastic approximation and instead increase the number of cycles or the batch size for your criticality calculation. But when the feedback is very fast to calculate, like in my case, it was the xenon feedback, which is just a single equation to evaluate, then it makes sense actually to have many iteration steps, like hundreds or thousands, and compensate it by lowering the statistics for the Monte Carlo criticality solver. If you do that, you'll see that the calculation actually converges faster, it's more efficient. All right, so we have something like 5-6 minutes for questions. So if you have some question to me, you are free to ask it now.